So those who don't know me, my name is Abhinav Garg and I have secured All India Rank 1 in GATE Computer Science 2022. Right, and I'm currently pursuing my master's from IIT Bombay in the Computer Science department. So we will first start with easy questions, comparatively easier questions to get a hold of COA, and then we will move to more difficult ones, right? So question 1 is saying that which of the following is included in the architecture of the computer? So we know that COA consists of what? Computer organization and architecture, right? So architecture usually comprises of the CPU design, the different instructions that the computer will support, different instruction like the add instruction, the multiply instruction, the divide instruction, and so on. Right? So these are different types of instruction this computer will support. The third one is the addressing modes. Addressing modes, that is, if let's say if this is an instruction, right? And every instruction is divided into first the opcode, then the addressing mode, and then the information about the operands. About operands. Right. Now every instruction can have operands from different sources, right? So let's say if I am getting a operand from a register, so that will be a register based addressing mode, right? Direct register addressing mode. So that information will have to be told in the instruction itself that this instruction has to take the operand from this particular register, right? So these are addressing modes. And fourth one is data format. Data format. That how the numbers or how the characters will be represented. So if you have heard about the ASCII characters or the or other like the EBCDIC code, right? So how the characters will be represented, that has to be told to the computer, or how the numbers will be represented, that how the floating point number will be represented. So we have IEEE format, and how the signed and the unsigned number will be represented. Signed and the unsigned number, right? Like they will be represented in two's complement or one's complement. So this entire thing has to be a part of the design, right? So these all information are part of the CPU architecture or computer architecture. So these all are designed by the architect, like what will the design of the CPU, what instruction will the CPU support, what types of addressing mode will the CPU support, how the data will be represented in that particular CPU. So these are part of the architecture. Right, and organization what organization means is that how these different parts or how different components of a computer will interact with each other. So organization includes the memory organization, the IO organization, right? And how we can make this particular computer more efficient. So concepts like pipelining, right? So these types of concepts are part of the computer organization, that how different components of a computer will interact with each other. So I'm repeating this again, that computer architecture will include the design of the CPU, the instruction that the CPU will support, the addressing modes, and the data format, right? So if we see the question, it is asking for which of the following is included in the architecture of the computer. So first option is saying that addressing mode and design of the CPU. Yes, these are part of the computer architecture. Instruction set and data format. So what is instruction set? The instruction set architecture represents different types of different types of instruction that the CPU support. right? So instruction set is also a part of the architecture and the data format. So this is also a part of the architecture. The secondary memory and the operating system. These are not a part of computer architecture. So any operating system can be run on any architecture, right? So let's say if you have an architecture like if you have a x86 architecture, right? So you can run the Linux operating systems on it also, and you can also run Windows operating system. So this is not a part of the architecture. And secondary memory also, you can also have a HDD, a hard disk, or a SDD, right? SSD. You can have any of these on the same architecture of the computer. So secondary memory is also not part of the architecture of the computer, right? So, and what are part of organization? The memory organization, IO organization, and the concepts by which we can increase the efficiency of the computer, like the concept of pipelining, right? So you have to just revise what is architecture, what is organization, and what all constitutes the computer architecture and what all constitutes the computer organization, right? So let's move on to the next question. Question number two. So this is a very easy question. If you know a little bit about instructions also, you can solve this type of question. So consider a digital computer which support 16 to address instructions, right? So first of all, when you see such questions or instruction, draw the format of the instruction, right? So every instruction will have first of all the opcode and then the information about the instruction, right? So here we have not mentioned anything about the addressing modes. So we will skip about the addressing modes here, and it is following to address instructions, right? So it is to address instruction. So what are to address instruction? It means that there will be two fields. There will be two fields for the operands, right? So these fields can be information about the register or information about the, let's say if it is following register based addressing mode. So here the register number will be present, right? And if it is following immediate addressing mode, so the exact operand value will be present here, right? So these are information about the operand. So it is saying that if the address length is of 6 bits, right? So these are what? These are addresses, right? And these are of 6 bits, right? Now it is also saying that it supports 16 different types of instruction. So if we have 16 different type of instruction, 16 different instructions, right? So how many bits we require to to represent 16 different values, right? So we require 2 bits to represent how many values? 4 different values, 3 bits for 8 different values, and 4 bits for 16 different values, right? We can calculate this by log base 2 16, which is 4. So we need 4 bits for opcode. To explain it more clearly, so let's say if the computer is supporting 4 different instructions: add, multiply, subtract, and let's say divide. Right. Now, these different instructions, there should be a code for all these different instructions, right? Let's say if 0 0 is representing the add operation, 0 1 is representing the multiply operation, 1 0 is representing the subtract operation, and 1 1 is representing the division operation, right? So the hardware of the computer, when the CPU will run this instruction, the CPU will know that how many different type of instructions are supported by the CPU. So it will know that how many bits are the opcode, right? So it will take the that many number of bits and will be able to identify that what type of instruction is that, right? So if we now require 16 different instructions, so let's say 0001 represents add instruction, then multiply by 0000, right? Then subtract by 0010 and so on. So like this, 16 different values will be there for the code, right? I know I am explaining this clearly because I want you to be very confident this particular topic. So usually around 1 to 2 marks of question is generally present in the GATE exam from this concept of either instruction or the addressing mode, right? And these types of questions are very easy to solve. So don't you do not want to miss these marks if you want to improve the rank, improve your rank, right? So just try to revise this concept and see if you have not understood anything. Right? If you have not understood anything, you can ask your doubt on the app, on the exam prep tool app, or you can also ask your doubt on the Telegram channel. Right? So let's move on to question number 3. So this is also a similar question. Just pause this video and try to solve this question on your own once. So it is given that consider a digital computer which supports only two address instruction. So first of all, we will draw the instruction format. There will be one opcode and then two fields for addresses. Right. Now it is saying that only two address instruction, each with 16 bits. So the length of the instruction is given as 16 bits. Now if the address length is 5 bits, then the maximum and the minimum number of instruction that the system can support. So it is given that the address length is 5 bits, right? So if total number of bits is 16 and the number of bits for opcode is x, then the value of x will be what? The value of x will be 6, right? Now if we have 6 bits for opcode, then how many different values we can represent? That will be 2 raised to the power of 6, which is 64, right? And these are the maximum number of maximum number of instruction that the CPU can support. CPU can support, right? And what about the minimum? So this is very important. So the question is saying that a digital computer which supports. So it is saying that this computer supports two address instructions. So the minimum number of instruction that this will support will be 1, right? It will not be 0 because here it is written that this computer supports two address instruction, right? So this means that 0 cannot be the answer. So the minimum number of instructions supported by this type of computer will be 1. So maximum will be 64 and minimum will be 1, right? So let's move on to question number 4. So a processor has 40 distinct instructions, right? So what information can we get from this? That how many bits will be required for the opcode? It will be log base 2 40, right? Now, since we know that this will be a decimal value, so what we will take, the seal value or the floor value? We will take the seal value, right? Why? Because let's say if we take the floor value, then the answer will be 5. If we take floor value, then answer will be 5, right? Because, right? But let's say if we take only 5 bits, then we will be able to represent only 32 values, right? And what we want is we want at least 40 different values. So if we want at least 40 different values, we will have to take the seal value. So this will be 6, right? So if we draw the instruction, so here the instruction format is given in the language. So it is saying that it is a 32-bit instruction. So the length of the instruction is 32 bits and it has an opcode. So it has an opcode, then two register operands. So there are two register operands and an immediate operand. Right? What do they mean by register operand? That the register number will be written here, right? So let's say if this particular computer has, let's say 16 general purpose registers, right? So these register can store different values, right? Now every register will be given some number, right? So this register will be 0000, then this will be 0001, then this will be 0010, and so on, right? Why four different bits? Because we had 16 different registers. So this register number will be stored in this particular field, right? And what is the immediate value? That the exact value that will be used in the instruction will be stored here, right? So let's say if the instruction is add R1, R2 and let's say 5. So this is the instruction that is described here, right? And so let's say this is the register R1 and this is the register R2. So it will take the value from R2, add 5 to it, and it will store the value in the R1 register, right? So I'm explaining this to you because I want you to be very clear that what are the different types of field that the instruction can support, right? And what does these fields mean? So this is very important because if you get a different question, which is right where you require this information, you will be able to solve that particular question very easily. So here in this question, there are 24 general purpose registers, right? So this particular processor has 24 GPRs. That means that how many bits will be required? So ceil of log base 2 is 24, that is 5 bits will be required to number these different registers. So 6 bits for the registers, and since we had 40 distinct instruction, the number of bits for opcode was 6 itself, right? And let's say the number of bits required for immediate field is x, right? So 6 plus 6 plus 6 plus x is equals to 32, and this means x equals to 32 minus 18, right? So this will be what? This will be, sorry, this will not be 6, this will be 5. We calculated the number of bits for register is 5. So this will be 6 plus 5, and that will be 32 minus 16, which is 16, right? So number of bits required for the immediate operand, or the number of bits for the immediate operand is 16, right? So for these types of question, just draw the instruction format. Just try to get the number of bits required for each of the field, and you can calculate the missing values by just adding the bits for all different types of field, right? So try to be very confident with these types of question. You don't want to lose 1 to 2 marks in the GATE exam. And you should be able to solve such questions in 1 minute. Right? So moving on to question number 5. So question number 5 says a CPU has 24-bit instructions. So every instruction is of 24 bits, right? Or we can say 3 bytes. Now a program starts at the address 300. So let's say if this is our main memory, then there is a program. So this is address 0, 1 and so on till 300, right? Now there is a program which starts at 300 and it is stored in the main memory like this, right? Now, which of the following is a legal program counter value, right? So what is program counter? Program counter is a special purpose register which stores the address of the next instruction to be executed, right? To be executed. So which one of the following will be a legal program counter value? So let's say if this particular instruction starts at 300, right? So this instruction is of how many bytes? 3 bytes, right? And here it has been given that, so nothing is mentioned about the type of the memory. So we will assume that this is a byte addressable memory, right? So this means that this instruction will be stored at the address 300, 301 and 302. So this will be instruction number 1, right? And after that on addresses 303, 4 and 5, the instruction I2 will be stored. So and so on, right? Now the program counter will store the starting address of the instruction because that is the address from where the instruction will be fetched. So this means that the value of the program counter can be 300 or 303 or 306 and so on. So that means it should be a multiple of 3 starting from 300, right? So can 400 be a legal program counter value? No, because this is not a multiple of 3. So this is not an answer. Can 500 be a legal program counter value? No, again this is not a multiple of 3. Can 600 be a program counter value? Yes, because it is a multiple of 3 starting from 300, right? And this will be what? Here, this will be a static address of the instruction, right? Can 700 be a legal program counter value? Again, no, because this is not a multiple of 3, right? So what are the concepts that you should know here? You should have known about the concept of program counter, right? Different types of memory, the byte addressable and the word addressable memory, right? And that the program counter stores the starting address of the next instruction, right? So answer will be here option C. So for clarity, let me first also explain that what is byte addressable and what is word addressable memory. So let me explain this here. So byte addressable and word addressable, right? Now if this is our memory, right, and this is byte number 1, byte number 2, byte number 3 and so on. So if every different byte is given a separate address, that means that this is a byte addressable memory, right? And if this is our memory, and let's say it is given that the word size was equals to 2 bytes, right? Now if these are different bytes, now every 2 byte will be given a separate address, right? And that means that this particular byte and this particular byte will have the same address, right? So this is a type of word addressable memory, right? And byte addressable memory is equals to word addressable memory with word size equals to 1, right? So just try to remember this concept of byte addressable memory and word addressable memory. So let's assume that if here it is given that the memory is a word addressable memory and the word size is let's say 2 bytes, right? Then try to calculate the value of the legal program counter value, right? So this is a homework question. Try to see if you are able to solve this question, right? You will be able to see if you are clear with the concept of word addressable memories. So let's move on to question number 6, right? So this is a question on the addressing modes. Addressing modes. So pause this video and try if you are able to solve this particular question. So here it is given that for computer based on 3 address instruction format, right? So we have 3 address instruction. That means there will be 3 fields for the operands addresses, and we will have an opcode. So this is our instruction format, right? Now each address field can be used to specify which of the following, right? So a memory operand. So it is saying that which of the following. So these address fields can be used to specify which of the following, right? So option S1 is saying a memory operand. A memory operand. So this is true. Why? Because if we use the direct addressing mode, direct addressing mode, then this address field will contain the address of the memory location, right? Address of the memory location. Let me write this here. Address of memory location. And the operand will be stored at that particular memory location. And S2 is saying that a process register. So this is also true. If we are using register based addressing mode. Addressing mode. So for that, here, for in the field of address, the register number will be stored. Register number. So if the computer has 64 different registers, that means that a 6-bit 6-bit information will be stored in this particular field, right? The third is saying an implied accumulator register. So this is false. Why? Because in implied mode, no information, no information is mentioned in the instruction about the operand. About the operand. That means that only the addressing mode will be told in that particular instruction, and nothing will be mentioned about the operand itself, right? And the instruction and the CPU will be smart enough to see that it requires the value from the accumulator. So an example of such type of instruction is the INCA instruction, that is the increment accumulator instruction. So nothing will be mentioned about the operand in those types of instructions, right? So S3, this is false. S1 and S2 is true. So answer is either S1 or S2. Option A. So you should know different types of addressing modes. Different types of addressing modes. Let me just describe in brief. So the first one is the implied mode, right? So these types of, in this particular instruction, in these types of instruction, nothing is mentioned about the operand. So nothing is mentioned about operand in the instruction, right? So the effective address of that particular instruction or that particular operand will be taken implicitly. The second one is the immediate mode, represents that the operand itself is stored in the instruction, in the instruction, right? The third one is the direct mode. The direct mode says that the address of the operand is stored. What type of address? The memory address. Right. So let's say if this is our memory and our operand is stored at, let's say, memory location 3000. Right. So this 3000 value will be present inside the instruction. So, and the value will be stored at this particular memory location. The fourth one is the indirect mode. Indirect mode. Now, the address of operand is stored in the memory location. In the memory location. Right. So let's say if this is our memory and our operand is stored at, let's say, the address 6000. Right. Now there will be another memory location, let's say 3000, and this will store the value 6000, right? And this value 3000 will be stored in our instruction, right? So these types of addressing mode supports the concept of pointers, right? So pointers follow a similar concept, right? And fifth one is register mode. Here the register number is stored in the instruction, right? The sixth one is the register indirect mode. Again, now here what will be done is that the address or the memory location will be stored inside the register. So let's say if this is register number 1. So here the memory location will be stored. So let's say if our operand is stored at memory location 3000. So this register will store the value 3000, right? This is the register indirect mode. So there are more addressing modes like auto increment decrement, PC relative mode, base register mode, right? So you should be very thorough with these addressing modes, these 8 or 9 addressing modes, right? So you should not miss even a single thing from these addressing mode, right? These are very important, and these can help you to score at least 1 mark or even 2 mark from the GATE exam, right? So be very thorough with these addressing modes. So let's move to question number 7. Right. So this is a similar question to the previous ones. Just try to solve this question on your own once. So it is given that a machine has 32-bit architecture. So again, here is a new concept. So I have chosen the question in such a way that you learn something new from each and every question, right? So I want you to revise these concepts. These are small things but can help you in the GATE exam. So what is the difference between, what is the 32-bit architecture first of all? What is the 32-bit architecture? So if it is given that there is a 32-bit architecture, this means that the word size is 32 2-bit, right? So if it was 64-bit here, then the word size would have been 64 bits, right? So you have to remember that what type of information you have to take from what type of language, right? So here it is given that a machine has 32-bit architecture. This means that word size is word size is 32 bits. Now, with one word log instruction, right? So here, if you did not know this concept, you will be confused, right? That what is the word size? So the word size is hidden here. Now it is given that the instruction size is one word long, which is 32 bits, right? Now it has 64 registers. So if it has 64 registers, then the number of bits for numbering the registers will be for numbering registers will be what? Log base to 64 seal, right? And this will be 6. Now each of which is 32-bit long. So it is saying that even the register, now let's say if this was register R1, so this R1 register can store a 32-bit value, right? Now it needs to support 45 different instructions. So number of bits for opcode will be what? Log base to 45 seal, right? And that will also be 6. Now which have an immediate operand in addition to two register operands. So the format of the instruction is given as there is a opcode, two register operands and one immediate operand, right? So the number of bits that we required for numbering the registers were 6. So 6 for this field and 6 for this field and also 6 for the opcode, right? Now for the immediate value, if the number of bits for the immediate value is x, this means that 18 plus x equals to 32 and x equals to 14, right? Now the question is saying that assuming that the immediate operand is an unsigned integer, right? If it is an unsigned integer, then the maximum value of the immediate operand, right? So here if you know the concept of what the maximum or the range of unsigned integers, range of unsigned integers, right? So if we have a x bit unsigned integer, then the range will be what? 0 to 2 raised to the power of x minus 1, right? So these are the range of unsigned integers. And here we got the value of x as x was 14. So that means 2 power 14 minus 1, right? Now again you should remember some values of 2. So you should remember the powers of 2 as 2 power 10 is equals to 1024, 2048, 2 power 12 equals to 4096, 8192 and 2 power 14 equals to 16384, right? You should remember at least till 2 power 14. This will save your time. You do not have to use the calculator to calculate these power of 2. You should remember these because these are some highly used values of 2, right? You should also remember the values till 2 power 9, right? So at least remember powers from 2 power 1 to 2 power 14 to save some time in the GATE exam. So here, if you use this value of 2 power 14, that will be 16384 minus 1, that is 16383. Right, so the answer will be option A, right? So concepts here were you should have known the range of unsigned integers, unsigned integers. Just try to get the concept behind this range of unsigned integers. Don't try to just rote learn this formula, right? You should have also known that how many bits we required for numbering the registers and what is an instruction format. So these were the concepts that you require to solve such questions, right? And also try to remember these powers of 2 because you want to save some time in the GATE exam for difficult questions, right? So let's move on to question number 8. So it is given that consider a hypothetical processor with an instruction of type LWR1 and 20R2. So the instruction is given as LWR1, comma 20R2. So which during execution reads a 32-bit word from a memory and stores it in a 32-bit register R1. So it is saying that this instruction reads a 32-bit value from the memory and stores it in a 32-bit register. Now the effective address of the memory location is obtained by addition of a constant. So first of all, what is effective address? Effective address, right? So if it is a arithmetic operation, right? So if it is an arithmetic operation, the effective address is the memory location of the operand, right? The address at which this operand is stored is the effective address of that particular operand, right? And if it is a these are for arithmetic operations, and if it is a branch instruction, if it is a branch instruction, then target address the target address of the branch, right, is the effective address of these types of instructions. So there are the different definitions for arithmetic instructions and the branch instructions, right? So you should remember this concept of effective address. So it is saying that the effective address of the memory location is obtained by addition of a constant 20 to the contents of register R2. So R2, so the value stored at R2 plus 20. So let's say if this is the value stored at R2, value at R2 plus 20, right? Now you get what? You get the effective address, right? What that mean is, let's say if the register R2 stores the value of 3000, right? That means the effective address will be 3020, right? And the value will be stored at this particular location, right? The operand will be stored here. So which of the following best reflects the addressing mode represented by this instruction for operand, right? So it is saying that which of these options represents the addressing mode mentioned in this particular instruction. So option A is saying that immediate addressing, right? So this is wrong. Why? Because in immediate addressing, the effective address or the operand itself is stored in the instruction, right? So here we do not have a concept of effective address, right? So the option A is wrong. Second is saying that register addressing. So in register addressing, we do not add anything, right? We do not add anything. We directly take the value from the register itself. So let's say, so here the operand is stored inside the register itself, right? So this is also wrong. The third one is saying that register indirect scaled addressing, right? So this is also wrong. Why? Because in this type of addressing, what is done is that, let's say if this is a register, let's say R1. Now it is the register indirect scaled addressing, right? So here let's say if a value, if a value 3000 or the value, let's say 5 is stored in this particular register, right? Now what will be done is a base value plus 5, that is the value stored in this register, into some scaling factor, right? Into some scaling factor will be taken. Now this base value can be a part of the instruction itself, or there can be a base register for it, right? And this scaling factor will be taken implicitly implicitly by the CPU. Now this will give us what? This will give us a memory location, right? And that particular memory location, let's say this gave a value of 3000, and at that particular memory location, another memory location will be stored, let's say 6000, and at this particular memory location, our operand will be there, right? So this is how we are going to get our operand in this particular addressing mode, right? So are we doing this in this particular instruction? No. So this is also wrong. The fourth option is saying that base indexed addressing. So this is correct. This is correct because in base index addressing, what we do is, so we have a base register which will store the base address, or we can have this base address in the instruction itself, and then we will have an index register which will store the index, right? And we will get the effective address by using this formula, that base address plus the index value, right? So this is what we are doing here. The R2 register is storing the index value, and right, so the R2 register is storing the base value, right? So R2 is our base register, and this 20 is a constant that we are adding to get to a particular index, right? So that is why option D is correct, right? So if you have any doubts, about the addressing modes that we have discussed, just ask this on this particular feature or the Telegram channel, right? Don't hesitate to ask your doubts, because that will that will help you to clear the concepts in a much more efficient way, right? So let's move to question number 9. Question number 9. Again, a question on addressing modes. Addressing modes. Right. So these all questions that we have solved, all these questions are PYQs, right? So if you are very clear with these addressing modes, you could have solved these questions very easily. So as I have told that, be very clear with these types of addressing modes, right? Now, in question number 9, it is saying that which of the following addressing modes are suitable for program relocation at runtime? Program relocation at runtime, right? So option 1 is saying as option 1 is absolute addressing. So this is another name of what? Direct addressing. Direct addressing, right? So in this addressing, in this addressing, so in this addressing, if this is our instruction, there will be an opcode, the code for the addressing mode, and the location. The location will be the memory location of the operand will be stored, right? Now, if we want to relocate, relocate this program, then we will have to change these values of memory locations, right? Because let's say if this is our instruction and it is stored at the memory location 3000, and the operand is stored at the memory location 6000, right? Now, if we want to relocate this particular program from 3,000 to 6,000 to, let's say, 9,000 to 12,000, right? So we will have to change this particular operand, the memory location of the operand for every different instruction, right? And this will take a lot of time. So this type of addressing mode does not support program relocation at runtime. So this is false. The second one is the base addressing or the base register addressing. Base register addressing, right? So these types of instruction will what will these how the format will look like. So there will be an opcode, again the code for addressing mode, right? And then after that we will have the offset value or the index value, right? And then we will have what? We will have a base register which will store the base address of the, let's say if you are accessing an array, so base address of the array, right? So even if we relocate a program from here to here, the offset of the array will be same, right? So if we wanted to access, let's say, 10th element of the array, so even if the base address is changed, the 10th value will be stored at a distance, what will be stored at base address plus 10, base address plus 10 into the size of element, right? So even if we relocate this program, we will not have to change these index values, right? That is why this type of addressing will support program relocation, right? So this is correct. The fourth option is saying indirect addressing. Again, we will have to change the values, right? So let's explain this. So if this is our instruction, we will have opcode, again mode, and then what? Then a memory location for the operand is stored, right? Now, this particular memory location will store another memory location, right? And the operand will be stored at this memory location. So if we relocate this program to another locations, then what we will have to do is, first we will have to change these values, the memory location values in the instructions. Then we will again have to change what values? Then we will again have to change the values at these locations, right? Because this is again a new location. So that will again take a lot of time and we need to recompile the program to get the instruction, right? So this also does not support program relocation, right? Now we can get the answer from the options itself. So here we know that first and fourth cannot be the options. So this is gone, this is gone, and this is gone. So answer will be C, right? So this means that relative addressing also supports program relocation, right? So I'm leaving this for homework. So try to revise what is PC relative addressing mode, right? And like here we have devised that why these addressing modes do not support program relocation. Try to devise that why PC relative or the relative addressing supports addressing mode, right? So I want you to go through your notes. That is why I'm giving you this homework and try to revise PC relative addressing mode. This is a very important addressing mode, right? So if time permits, we will discuss this again in the next video that what is PC relative addressing mode, right? For now, just try to do it on your own once. So let's move to question number 10. Which of the following is not a form of memory, right? So here it is asked that which of the following is not a form of memory. So option A is saying that the instruction cache. So let's say if we are accessing, let's say if we have a for loop, which let's say increments I, right? Let's say which increments A, right? And this for loop runs for 10 times. Now we know that this particular instruction will be accessed 10 times, right? And now if we access this instruction from the memory, right, for 10 different times, it will take a lot of time. That is why a CPU has two types of cache, a data cache, and an instruction cache. So the instruction will be stored or cached in this particular cache, and the operands will be cached in this type of cache. So this is a hardware. This is a form of memory, right? So what we have is we have different levels of cache, L1, L2, and L3 cache, right? And these are hardwares. These are SRAM, right? So this is a form of memory. So this is true. Option B is saying that instruction register. So what are instruction registers? So these are again hardware on the CPU or on your motherboard, right? Which stores these instructions, right? So your CPU, your hardware can have n number of registers. So every hardware a different number of registers, and this is also a form of memory. So this is also true. Option C is saying that instruction opcode, right? This is false. Why? Because instruction opcode is not a form of memory. It is just a representation. So if this is an instruction format, the opcode and the info about the operands, right? Info about operands. See, opcode is not a form of memory. It is just a representation. Just a representation of a particular type of instruction, right? Let's say if the CPU supports the add instruction, like, right? So it will have, let's say, a 4-bit opcode which will be used by the CPU to identify that this particular instruction is a add instruction, right? So an instruction will be what? A binary code, right? So let's say if we have, let's say 10-bit instruction, right? Right. So now when we give this particular instruction to the CPU should know that what is this instruction, right? What this instruction translates to. And the CPU only understands what? The CPU only understands the binary code. So by a particular circuit, it will be able to know that the CPU already know that how many instruction it supports, right? That means it's know that how many bits are used for the opcode. By using a hardware, it will know that what type of instruction is this, right? It will use a, let's say, a decoder by which it will know that what type of instruction is this, and then by using another other hardware it will be able to extract the operands from this information, right? So this is how a CPU decodes an instruction. So this is false because this is just a representation of particular type of instruction. And option D is saying that translation leukocyte buffer. This is true. This is also a hardware. So TLB is a hardware which stores translations, right? What type of translations? So if you have gone with the OS RIC course or the OS complete course, you know that TLB stores translation from the virtual addresses to physical addresses, right? To avoid to avoid multiple main memory accesses. Multiple main memory accesses while walking the page table, right? While walking the page table. right? So if we have a multi-level paging, then we need to access the memory multiple times, right? And to avoid that, we cache these address translations in a TLB. So this is also hardware in the main memory or the memory management unit, right? So you should know these concepts at your fingertips, that what is instruction cache, what is instruction register, what is opcode, what is TLB, right? So here the answer will be option C. Moving on to question number 11. Again, a question on addressing modes. So if you are clear with what are these different addressing modes, then just try to solve this question once. So here we have been given that the most appropriate matching for the following pairs, right? So first one is the indirect addressing mode, right? So again, to revise, what is indirect addressing mode? The operand field, let's say, stores a value 3000, right? This will store another memory location value, and that particular memory location will store our operand, right? And these types of addressing modes are used to implement pointers. I've already told you that indirect addressing mode is used to implement pointers. So x will be matched to 3. The second one is saying that immediate addressing, right? So what is immediate addressing? If this is an instruction, the opcode, the mode, and the value will be stored inside the instruction itself, right? So let's say if a value 20 is stored here itself. So these types of instructions are used while using constants. Again, the y will be matched to, so here this was with pointer, so this is 2, and y will be matched to constants, right? And so the left one is 1. Let's revise this auto decrement addressing. So what is done here is that if this is an instruction, right? So there will be a register. Let's say if we are implementing a for loop, right? From I equal to 0 to, let's say I less than 10, I plus plus. So there will be a register which will store the current value, of I, right? So here it is the auto decrement operator. So this will be minus minus I, right? And this register will store the current value of I. And whenever we access this instruction, the index value or the memory location will be accessed from this particular register, and this will be auto decremented, right? So let's say if the value was, let's say, 3000, and we access this particular instruction, or we execute this particular instruction, then it will auto decrement this value, register value, to, let's say, 2099, right? So this will be done automatically, and the user won't need to, or the instruction does not need to tell the CPU explicitly to decrement this value, right? So this is auto decrement addressing. So that is why the answer will be x2 y3 z1. So that will be option C. So again a note. So this is to remember that the auto increment mode does a post increment operator. Does a post increment operation. And the auto decrement mode does a pre decrement operation, right? Just remember this information. This can help you in some questions. I have seen some few PYQs where this particular information was important, right? Also, if it is written anywhere that a particular CPU follows mnemonic addressing mode, right? So this means that it is following an implied addressing mode. This is another name for implied addressing mode, right? So I will try to give these small information or these small points throughout this course. So let's say if we are solving some question on cache or some pipelining, then I will try to include such points or such small points which can help you to avoid silly mistakes, right? Or which can help you to gain some more marks. So just try to remember these 3 points. So let's move to question number 18. So this is some new type of question. This is a question on data transmission. Data transmission, right? So here it is given that how many 8-bit characters can be transmitted per second. So it is asking for the transmission speed, transmission speed over 9600 bits per second serial communication, right? So let's say if this is our interface. So this interface is having a speed of 9600 bits per second. Bits per second transfer speed, right? That means that this particular interface can transmit bits on the bus or the line at a speed of 9600 bits per second, right? Now, this particular serial communication link uses a parity synchronous mode of transmission, right? So, we also need a synchronization mechanism, right? So let's say if these two interfaces are communicating with each other, then there should be a mode to synchronize these two interfaces, right? So let's say if this particular interface starts a message and then it starts sending the message. So this interface will need a particular information that the message has been started and then the message will be stored here. So let's say if this is a message format, so initially there will be some start bit, right? To inform the interface, the receiving interface, that the message has been started, right? And after that, there will be the message or the character, and after that, there will be stop bits, right? Why stop bits? Because let's say if we transmit two different messages, then the receiving interface should be able to distinguish between these two interfaces, right? So if these two messages are sent one after another, then there should be some mechanism for this receiving interface to know that this message was till here, and after that the second message has been started. So there are stop bits at the end of each message, and there are start bits at the starting of each message, right? So this is how two different interfaces synchronize with each other, right? So here we have been given that the synchronization mechanism uses one start bit, then 8 data bits, and then two stop bits, right? And there is also one parity bit. Why this parity bit? Because for error detection, right? For error detection. So let's say if we are transferring this message on, let's say, a wire, right? So there can be different ways by which there can be attenuation on this particular messages. The bits can flip, the message can be corrupted, right? So we need some mechanism to detect these errors also. So that is why there is a parity bit also included in the message. So every character here is being transferred like, first there will be a start bit, then a character, then stop bit, and the stop bit will be in the last, and also a parity bit, right? So it is given that start bit is of 1 bit plus the characters are of 8 bits, right? 8 character bits, then 2 stop bits and 1 parity bit. So that means it is 9 plus 3, which is 12, right? So every message or every character will be transferred by 12 bits of transmission, 12 bits per character, right? Now the transmission speed given was 9600 bits per second, right? So number of characters per second will be transmission speed, in bits per second divided by the number of bits per character, right? Number of bits per character. So this is 9600 bits per second divided by 12 bits per character. So this will be what? This will be 800 characters per second, right? So this will be our transmission speed. So answer will be 800, right? So I've explained the concept of transmission in brief here. If you have any doubt with this particular concept, you can just go through your notes once, or you can use the raise your doubt or ask your doubt feature on the app or on the Telegram channel. Right, I highly encourage you to ask your doubts, because if you do not ask your doubts, you will be stuck with your problem, you will be stuck with your doubts, and you can make the same mistake again in the GATE exam, right? So these types of questions are usually asked for 1 mark, right? And if you know this particular concept, then this question is like a cakewalk, right? This you can solve this question in like 30 seconds or let's say 1 minute, right? So let's move to question number 13. Again, this is a question on transmission speeds or transmission on data transmission. Let's try this question on your once if you have understood the concept that I have explained. So when synchronous serialization communication is employing what? So it is a synchronous synchronization communication is employing, sorry, this was not visible. So it is saying that asynchronous serial communication is employing 8 character bits, 1 parity bit, 2 start bits and 1 stop bit, right? So if we draw a message format, then there are 2 start bits, 2 start bits, then we have 8 character bits, and then 1 parity and then 1 stop bit, right? So the overall size of a message will be 8 plus 2 plus 2, that is 12 bits, right? To maintain a rate of 400 characters per second. So in the previous question, we were given the transmission speed in bits per second. Here, what we want is we need a transmission speed of 400 characters per second. 400 characters per second. The minimum transfer rate should be required is, right? So it is asking that what should be the minimum transmission speed of an interface. Transmission speed of an interface to achieve 400 characters per second, right? To achieve a transmission speed of 400 characters per second, right? So how can we solve this question? So let's say if we have a transmission speed of x bits per second, x bits per second, right? Now we know that the transmission speed in characters per second the transmission speed in characters per second is calculated as the transmission speed in bits per second divided by the number of characters or the number of bits per characters, right? So the transmission speed in character per second is given as 400. This was assumed as x and divided by the number of bits per second we have calculated as 12 bits, right? So this will be 12, right? So the answer will be 12 into 400 bits per second. That will be 4800 bits per second, right? So, right, if you do not know this concept, you will have to remember these formulas, right? So I don't want to remember these formulas because there are much more important things to remember in the GATE exam. So don't try to remember these formula. Try to understand this particular concept to solve questions on data transmissions, right? These questions are very easy and can get you 1 mark or 2 mark in the GATE exam, right? So if you see such question, you should not miss it because you have seen the concept and you have solved many questions on this particular topic, right? Let's solve one more question on this particular topic. So yeah, this is question number 16. Let's solve this first because this is of the similar topic. So how many 8-bit characters can be transmitted per second over a 9600 baud serial communication, right? So what is baud? So baud is that the transmission speed the transmission speed in data units per second, right? Data units per second, right? So this is similar to bits per second. However, instead of bits per second, we will have data units per second, right? Now here the data unit is not given here, so we will assume that assuming that one data unit is equals to 1 bit, right? So we can say this is a transmission link with the speed of 9600 bits per second, right? Now the character size is given as what? 8 bits, and the transmission or each message will have one start bit, 8 data bits, 2 stop bits and 1 parity bit, right? That means that every message will contain one character of 8 bits, one start bits, one character of 8 bits, 2 stop bits and 1 parity bit. This is again what? 8 plus 2 plus 1 plus 1, which is 12. That means that 12 bits per character will be transferred, right? Now we will have to calculate how many characters can be transmitted per second, right? Again, we will have to calculate the transmission speed in characters per second, transmission speed in characters per second, and that was transmission speed in bits per second divided by number of bits per character. So that will be 9600 divided by 12 characters per second, right? That will be 800, right? So option B. So here, just remember what is baud. Don't get confused with what is baud here. So I've explained baud is nothing but the transmission speed in data units per second, right? So if it was mentioned that what is data units, you can calculate the value in bits per second by using the value of data units, right? That how many bits are there in one particular data unit, you can solve that question in that particular manner, right? So let's move on to the question number 14, right? So again a question on addressing modes. Try to see if you understand these three different types of addressing mode, right? So try to solve this question once. So we have to match the first column with the items in the second column. So first is indirect addressing, right? So I have explained this indirect addressing modes enough number of times. So we can say that this is used for writing relocatable code, right? So this will be right. So this will not be writing relocatable code. Again, I have explained this you in the previous question. So I have explained this in one of the previous questions. So right. So I have explained this in there was a question that let me see. Okay, so there was a question that which of the following addressing modes supported writing relocatable code, right? And I explained that indirect addressing mode cannot support writing relocatable code because if we see the memory location is stored in the instruction and that particular memory location stores another memory location which stores the operand value, right? Now, if we relocate this code, then we will have to recompile this code because the memory location would have changed, right? So, indirect addressing is used for passing array as a parameter. Why? Because when we pass array as a parameter, we use the concept of pointers, right? And we know very well that indirect addressing supports the concepts of concept of pointer, right? So x will be matched with 3. Then y is what? Y is index addressing, right? So what is indexed addressing? So it can support what? It can support array implementation, right? So y supports 1 and base register addressing is used for writing relocatable code, right? So I've already explained that why this base register addressing supports writing relocatable code. So index addressing, what it does is that let's say we will have a index register, right? And this particular, let's say if this is an instruction, we will have an opcode, the mode, and in index addressing, we can have two different types of index addressing. We can have one with base address in the instruction, or we can have a separate base register, right? Now, if we want to access, let's say a of 10, right? Then the base address value of this array a, base of a will be stored in this base register and the value 10 will be stored in this index register, right? We can also have these index value and the base value in the instruction itself, right? So we can have two different types of implementation of these instruction, and then we can calculate the effective address by addition of the base address plus the value in the index register, right? So this is how we can use this type of mode for the implementation of arrays, right? So answer will be x3 y1 x3 y1 z2. So that will be option A, right? So I got a little confused here that it supported this, but this does not support it, as I've already explained it in the one of the previous questions, right? So let's move to question number 15. Right, so see, these types of addressing modes are very confusing. So there are a lot of addressing modes and sometimes even I get confused. So just try to be very clear with these addressing modes, right? So question number 15 says that a processor has 64 registers and uses 16-bit instruction format, right? So if first let's first of all calculate number of bits for register numbering, right? So it will be log base 2 64, that will be 6, right? Now this type of processor supports two types of instruction, right? So this is one new different type of question with two different type of instruction supported, right? And these types of questions are usually asked for 2 marks. So let me explain that how you can solve these types of question. So first we will draw the format for both types of instruction. So this is, let's say, first type of instruction and the second type of instruction, right? So let's say this is the I type and this is the R type. Now each I type instruction contains an opcode. So the format is as follows. First an opcode, a register name and a 4-bit immediate value. So 4-bit immediate value. So let's write it as immediate, and this is of 4 bits, right? And each R type instruction contains an opcode. So for R type, the format is opcode, then 2 register names, and that's it. So the format is like this for R type instructions, right? We have already calculated the number of bits for register number. Register name is 6. So 6 here, and 6 here, right? Now the instruction length was given as 16 bits. So this was also 16 bit. This was also 16 bits. So the opcode for R type instruction will be, the size of the opcode for R type instructions will be 16 minus 12, which is 4. And the length of the opcode for I type instruction will be 16 minus 10, which is 6, right? Now it is given as if there are 8 distinct I type opcodes. So different type of opcodes of I type is 8. Then the maximum number of distinct R type opcodes are, right? So what you have to do is you have to start with the opcode of the least length, right? So you can use this type of method to solve if even for 3 different type of instruction. So we will start with the least value and we will see that how many maximum number of opcodes can be there for that particular value. So here this will be 2 power 4, that is 16, right? Now out of those, let's say the used opcodes were X and the unused were 16 minus X, right? Now just go to the next immediate bigger value, and out of those next immediate bigger values, 4 bits were already used by the first type of instruction and 2 bits were remaining, right? Now these 4 bits could have represented what? Could have represented 16 different values. However, out of these 16 different values, X values were already used, right? So that means that 16 minus X values can be used for opcodes of I type, right? So this means that the distinct number of opcodes, the total or the maximum number of distinct number of opcodes for I type will be 16 minus X into 2 square, right? Because let's say these were 6 bits, 3, 4, 5, 6, right? So these 4 values would have represented 16 different values, right? But out of those, X values were already used, right? So we cannot use the same values in the opcodes of I type, right? And 16 minus x values could only be used now with these two bits, these 16 minus x values. Let's say if this is one of the unused values, now with two different more bits, we can have four different opcodes, right? 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, and 1, 1, right? Now, similarly, there can be 16 minus x values here and two square values here. So this is the maximum number of opcodes for I type. So that this is this, right? Now, what we want, the question is saying that there are 8 distinct I types, right? So this means that this particular value should be greater than or equal to 8, right? Because it is saying it supports 8 distinct I type instructions. So if we solve this, this will be 8 divided by 4, which is 2, and 16 minus 2. So x should be less than or equal to 14, right? So these are the maximum number of R type instructions. R type instructions, right? So the answer for this question will be 14, right? So to revise, what you will do is just write the format for all different type of instructions. Let's say there were 3 different type of instructions, right? Then try to calculate the length of the opcodes. Let's say if this was X, this was Y, and this was Z, right? Then go to the smallest value of opcode. Let's say if this X is the smallest out of all 3, and calculate the maximum, the total number of opcodes that these can represent, right? And then calculate the, either this information will be given or you would have to calculate this, right? So you can, if you have to calculate this value, then take it as a variable, otherwise use it as a constant. Then calculate the used values and then the unused values or the unused number of opcodes, right? Now, out of these y different bits, let's say if this was the second biggest value, then out of this y different bits, x bits have been used, then y minus x bits were remaining, right? So total will be, let's say if this unused were w, so w into 2 power y minus x, right? Then again, we knew this information, right? The use number of the second type of instruction, or if we have to calculate this, just take it again as a variable and then calculate the unused, right? So if this is, let's say if this was 2 power x, the used were, let's say a, so unused will be what? Unused will be 2 power x minus a, right? Now the total here will be 2 power x minus a into this, right? And used for y, let's say, is b. So unused will be 2 power x minus a, y minus x minus b, right? Now again, for z, if z is the largest address or largest opcode out of these 3, for z you can calculate, first of all, divide z as y and z minus y, right? And what you can do is you can calculate the total by the unused value, right? So let's say if this was psi, so this will be psi into 2 power z minus y. Again, you can use the used values and calculate the unused values, right? So this is how you can solve the question which supports multiple types of instructions, right? So try to solve such question. There are some PYQs which have multiple types of instructions supported, and 2 marks are guaranteed. 2 marks are guaranteed if such question comes in the exam, right? So if you know this particular concept, you can solve this question very fast, right? You will not be confused that what is, even if there are more number of instructions, more types of instructions supported, right? So just try to solve more PYQs of these type, right? So if you have not understood the concept, try to rewatch this, try to solve some question. If you still are unable to solve, then go on the Telegram channel or raise your doubt on the app, right? So I will be very happy if such question comes in the exam and if I am able to resolve your doubt, right?